Welcome to this video on Year 2 Statistics, Chapter 1 Prep Practice on Modeling, Correlation and Hypothesis Testing of Correlation. Question 1. Log Y versus log data is plotted. A linear regression line for this coded data is found to have a good fit, and the gradient is 0.3 and the vertical intercept is minus 0.2. Write down the equation of log Y on log X regression line. Log Y on log X means log Y from log X. So think of log Y as the output and log X as the input. And then thinking about Y equals mx plus c, where Y is the output and X is the input, we get log Y equals 0.3 being the gradient, log X plus minus 0.2, where C is minus 0.2. And then write down an expression for Y in terms of X based on this information. We have log Y in terms of log X. So to try and get Y, we can do a variety of things. We can take 10 to the power of both sides, or what I've done here is the right-hand side I've simplified into a single logarithm by bringing the 0.3 in, and then writing minus 0.2 as being log of 10 to the power of minus 0.2, and then that log plus this log added together gives you a single log of the two numbers multiplied together. And therefore now, if you have log of Y equals log of this, that means that Y equals this. And then 10 to the minus 0.2 being about 0.631 means that this relationship in A becomes a relationship in B of Y being 10 to the minus 0.2 or approximately 0.631 x to the 0.3. Quite a useful thing to be able to do, to be able to move between logarithmic relationships and exponential relationships. Question 2. XY data is thought to satisfy a Y equals A times B to the power of X relationship. Find the appropriate coding, what variables should be plotted to obtain a linear relationship. So this is the opposite of question 1. If we take logs of this relationship, we get log of the left-hand side equals log of the right-hand side. And then using log rules, log of A, B to the X is log of A plus log of B to the X. And then log of B to the X becomes X log B. And so we get log of Y equals log of A plus X log B. And so looking at the variables, we would want to plot log Y versus X. If we do that for part B, then we should find that the log B is the gradient and the log A is the vertical intercept. So plotting log Y against X, if that relationship holds, then we should get a straight line, and that straight line should have a gradient of log B and a vertical intercept of log A. Question 3. Gary compared the total attendance X at home matches and total number of goals Y scored at home during a season of each of 12 football games playing in a league. The product moment correlation coefficient of this is 0.763. Helen was given the same data to analyze. In view of the large numbers involved, she decided to divide the attendance figures by 100. She then calculated the product moment correlation coefficient between X over 100 and Y. Write down the value Helen should have obtained. So if we have the correlation coefficient of 0.763 for data, but then we have X over 100 and Y, what will the correlation coefficient of that be? And the simple answer is that correlation is unaffected by linear coding. So you get exactly the same correlation coefficient. We'll find that the regression line changes, but the correlation coefficient does not change by linear coding. Question 4. The table shows data on the number of visitors to the UK in a month, V, visitors in thousands, and the amount of money they've spent, M, in millions of pounds, for each of 8 months. The product moment correlation coefficient between M and V is 0.962. Give a reason to support fitting a linear regression model of the form M equals A plus BV to this data. Well, if you have a correlation coefficient of 0.962, that's pretty close to 1, which indicates that the data lies pretty close to a straight line. In this case, because it's close to +1 to a straight line with a positive gradient. And so it makes sense to fit a line of best fit if the data fits quite well to a straight line. The M on V regression line is calculated to be M equals minus 467.2 plus 0.74 V, given interpretation of the 0.740. Well, that is the gradient, which basically means in general, for dy dx, or y in terms of x, it's the increase in y as x increases by 1. So in this case, it is what we expect M to increase by if V increases by 1. So looking at the units, that basically means that an increase in V by 1 is an increase of 1,000 visitors, and that will be associated with an increase of 0.740 million pounds in that month. And then if we rescale that, that basically means 740,000 in terms of pounds rather than millions of pounds per 1,000 extra visitors, which then divided by 1,000 means about 740 pounds extra money spent by each visitor or additional visitor would be expected on average. For the following significance tests, an extract is included at the bottom of this page with the critical values. So winding down, you can see them here. So expect to see that in the formula booklet. In fact, it's about the only table you now need from the formula booklet because everything else is available from the calculators. A sample of 16 values of X and Y are taken to test at the 10% significance level whether there is a positive correlation between X and Y. What's the critical region of PMCC? Well, the null hypothesis is always that the correlation coefficient is 0. In this case, because we're testing to see if it's positive, we're testing to see if the correlation coefficient is greater than 0. That means it's a one-tailed test. We're not checking to see if it's negatively correlated. And if we look at the table, 16, 10% one-tailed, we look at 16, and then we look at 10% one-tailed, the same as 5%. Sorry, 10% one-tailed is 0.3383 because it's all in one tail. And so the critical region for positive correlation that would essentially occupy 10% would be any value of R greater than 0.3383 would in this case be significant. So if we get a problem correlation coefficient of 0.4, is that significant? Yes, it is, because it's in the critical region. It is greater than 0.3383 in this red region here. Question 6, a sample of 10 values of X and Y are taken. For those values, the PMCC is minus 0.55. Using a 10% significance level test, whether this is a correlation, there is correlation between X and Y. We're not testing for positive or negative, so this could be a two-tail test. As usual, the null hypothesis is that they're uncorrelated. The alternative hypothesis is that they are correlated, not just positive or negative, but either. So it's a two-tailed test. And so 10% significance level, two-tailed is 5% each side. So using the tables, we're going to be looking at 10 values, 5%. So looking at 10 values, 5%, we can have critical value of 0.5494. And because it's two-tailed, it will be in the critical region if the value is less than minus 0.5494 or greater than plus 0.5494. So if you have a value of minus 0.55, that is just within the critical region, and so that is significant. There is evidence at the 5% level, two-tailed, sorry, 10% level. So that should be changed out to 10%. 10% level, the X and Y are correlated. Of course, it was 5% each tail, but the total significance level is 10%. And so we conclude that H1 is true, and H0, that's uncorrelated, is not true. Okay, I hope that was useful.